Hello and welcome to CM 4563, group number 9, Self-Consolidating Concrete. Our group is made of James Bernetti, Aaron Griswold, Jacob Potts, and Kevin Richards. To give you an overview of this presentation, we have 6 questions. Question number 1 is examples of real-time applications of SEC and success stories. Number 2 is what are the performance requirements for self-consolidating concrete mixture. Number 3 is what is the quality control test, which are used to evaluate a self-consolidating concrete mixture. Number 4 is what are the main rheological parameters that are measured when studying and designing an SEC mixture. Number 5 is how does SEC compare to conventional concrete in terms of mechanical properties and long-term durability. And number 6 is what are the limitations and negatives associated with using SEC in construction applications. The first part of our presentation is examples of real-time applications of SCC and success stories. To begin, I've listed 5 reasons to use self-consolidating concrete. Number 1 is that it eliminates mechanical vibration, and eliminating vibration in precast production settings reduces noise. In an urban setting, decreased noise may even allow for longer construction hours. Number 2, it improves concrete consolidation. SCC's impressive flowability promotes successful consolidation around dense, concentrated reinforcement. For example, SCC makes it possible to successfully fill areas unreachable with internal poker vibrators. It allows for denser reinforcement, adding strength in the process. Number 3, it enhances finishes. Architects enjoy increased freedom of design for a number of reasons, including increased options in formwork orientation. SCC can also be placed in intricate molds that would not work with conventional concrete. Number 4, it makes pumping easier. Higher slumps and excellent flowability promote easier pumping, including pumping to substantial heights. Quicker truck to pump discharge speeds up the construction process. And number 5, it saves money. When you use SCC, both direct and indirect cost savings occur from decreased construction times, lower discharge and placement times, cosmetic repairs that otherwise take time, and less wear and tear on equipment. So I have 6 examples of ways that SCC can be used. The first one is in high-rise building construction. The Burj Khalifa in Dubai utilized SCC for its concrete core and other structural elements. And this is the tallest building in the world currently, so it's pretty cool that SCC was utilized in creating that building. It also can be used in infrastructure repairs and retrofits. SCC is used for the retrofit of aging bridges and structures. A third way that SCC can be used is in architectural concrete applications. SCC is used to create intricate designs, such as the Banksy House in Prague, Czech Republic, and that is currently shown in the photo on this slide. It can also be used in precast concrete production. SCC is used to make precise and high-quality precast concrete elements. It can also be used in wind turbine foundations. SCC ensures the structural integrity of renewable energy structures. And it also can be used in nuclear power plant construction. Self-consolidating concrete was used in the construction of nuclear power plants to ensure its structural integrity of critical infrastructure. This table shows 5 recent success stories of SCC use, and a cool one that I wanted to point out was the number 1 subway line in New York City. It was another challenging SCC pour, and it was for a 3-foot thick slab under the number 1 subway line, which runs through the World Trade Center. A very heavily reinforced slab, 50 feet wide, was required, and the SCC mix was successfully pumped into this location blindly. Cameras were installed to observe the complete filling of the new slab. And on this side, I have provided the sources that I used. Thank you.
Hello, my name is James Barnett. This is CM 4563. I'm part of group 9. I'm answering questions 2 and 3. What are the performance requirements for self-consolidating concrete? Question 3, what are the quality control tests that are used to evaluate a self-consolidating concrete mixture? Well, self-consolidating concrete is a specialized variant of concrete that has been specifically formulated to possess the ability to flow and consolidate without the requirement of external mechanical vibrations or compaction. To achieve the intended performance of self-consolidating concrete, it is imperative to satisfy specific criteria pertaining to its properties and behavior. Performance requirements commonly encompass. So what are the characteristics of self-consolidating concrete and the quality control tests that are used to evaluate the mixture? Well, first we have flowability. To effectively fill intricate formwork, flow around reinforcement, and achieve self-leveling properties, it is imperative for self-consolidating concrete to possess a notable degree of flowability. Then we have passing ability. The SEC should possess an important level of passing ability, enabling it to navigate congested areas without experiencing segregation, thereby facilitating smooth flow. This aspect is of utmost importance in scenarios where intricate and heavily fortified constructions are implicated. Stability. Although self-consolidating concrete exhibits excellent flowability, it is crucial for it to maintain its stability and avoid excessive segregation or bleeding during the placement in its fresh form. Viscosity and rheology. Self-consolidating concrete must possess suitable viscosity and rheological characteristics to enable consistent flow and prevent segregation caused by gravitational forces. Viscosity modifying admixtures can be employed to attain the intended rheological properties. Slump flow. The SEC mixture ought to demonstrate a designated spread or slump flow, hence indicating its level of flowability. The unique project and application can influence the variability of the slump flow needs. Segregation and resistance. Self-consolidating concrete ought to exhibit resistance to segregation and the phenomenon, as this phenomenon might result in an uneven distribution of aggregate within the concrete mixture, characterized by an excessive concentration of aggregate in certain regions and a deficiency of aggregate in others. The assessment of segregation can be conducted by eye observation as well as through the administration of several tests. Strength and durability. To fill a specific application, it is imperative the self-consolidating concrete satisfies the prescribed compressive strength and durability criteria. To achieve satisfactory performance of self-compacting concrete, self-consolidating concrete throughout its service life, the mix design must consider the target strength class and exposure conditions. Compatibility with formwork. It is imperative that self-consolidating concrete exhibits compatibility with the formwork employed during the construction process. The material should not induce any structural harm to the formwork, and its capacity to flow should enable it to adequately occupy the formwork without generating empty spaces or obstruction. Aggregate gradation. The selection of aggregate gradation in self-compacting concrete should be conducted with caution to provide a well-balanced mixture that minimizes the potential for segregation. The utilization of well-graded aggregates is frequently employed to accomplish this objective. Air content. To attain the appropriate level of freeze-thaw resistance and workability, it is imperative to regulate the air content within the prescribed limits of self-consolidating concrete. It is imperative that the entrained air is uniformly dispersed. Types of tests for SCC. Well, first we have the slump flow. SCC should exhibit specified flowability, typically measured as slump flow. The J-ring or L-box test. The J-ring or L-box tests are used to evaluate the stability and passing ability of self-consolidating concrete. V-funnel tests. The V-funnel test measures the flow time of SCC through the V-shaped funnel and assesses its flowability. Visual Stability Index. The VSI is used to assess the stability and segregation resistance of self-consolidating concrete. It is often described in project specification and does not have a specific ASTM standard. Air content. The air content of SCC should be within the specified range, typically measured using ASTM C231-10. Rheological properties. The self-consolidating concrete's rheological properties includes viscosity and yield stress. May be evaluated using various test methods, but there is no specific ASTM standard for this. The assessment of self-consolidating concrete mixtures quality control often involves a compressive set of tests encompassing both fresh and hardened concrete properties. The administration of these tests is of utmost importance to ascertain that the SCC, self-consolidating concrete, satisfies the specified benchmarks for performance and durability. Quality control tests are vital for assessing the performance and durability of self-consolidating concrete to discover its compliance with the intended parameters. The following are many regularly employed tests for assessing the properties of a self-consolidating concrete mixture. This leads us to our third question. What are the rheological parameters that are measured when studying and designing an SCC mixture? How are they beneficial to the construction manager? Well, we have the slump flow again. The slump flow, the SCC should exhibit specified flowability, typically measured as slump flow, ASTM C1611-C1611M-14. Standard test method for slump flow, self-consolidating concrete. Then we have the J-ring or box, the L-box test. The J-ring or L-box tests are used to evaluate the stability and passing ability of the SCC, ASTM 1621-C1621M-12. The V-funnel test. The V-funnel test measures the flow time of SCC through a V-shaped funnel and assesses its flowability, ASTM C1611-C1611M-14. Visual Stability Index. The VSI is used to assess the stability and segregation resistance of SCC. It is often described in project specification and does not have a specific ASTM standard. It involves visual observation of the concrete during and after the pouring. Air content. Air content of SCC should be within the specified range, typically measured using ASTM C231-110. Rheological properties, including viscosity and yield stress, may be evaluated using various test methods, but there is no specific ASTM standard for this project. So basically, the slump flow test utilizes and assesses the flowability and workability of characteristics of self-consolidating concrete. This produces the procedure entails facilitating unrestricted flow of the self-consolidating concrete mixture and subsequently quantifies the diameter of the resulting concrete spread. The J-ring test is utilized to evaluate the flowability of self-compacting concrete in the presence of a densely packed reinforcement. The L-box test assesses the flowability of self-consolidating concrete in constrained areas and around obstacles. The T50 time parameter quantifies the duration required for the spread diameter of self-consolidating concrete to reach specific value during the slump flow test. The V-funnel test is a test method used to determine the flow time of self-consolidating concrete as it passes through a V-funnel shape configuration. Then we have visual inspection. The visual inspection plays a crucial role in ensuring quality control. The evaluation of SCC should encompass an examination of its visual characteristics, such as the identification of segregation, honeycombing, or any other observable flaws. The strength and durability test is imperative to conduct compressive strength testing on self-consolidating concrete because it verifies the compliance with the designated design strength. Samples are commonly collected and subjected to testing in accordance with the established protocols. In conclusion, these tests help ensure that the self-consolidating concrete meets the necessary performance, workability, and durability requirements for a specific construction project. The specific tests required may vary depending on project specification, local standards, and quality control protocols.
What are the main rheological parameters measured when studying and designing a self-consolidating concrete mixture? A self-consolidating concrete mixture is a highly fluid mixture designed to flow and consolidate under its own weight. It needs to be self-compacting, self-placing, and self-leveling. Because of this, there are three main rheological parameters considered in a self-consolidating concrete mixture. They are the filling ability, the passing ability, and the resistance to segregation. Let's talk about each of these rheological parameters individually. First, let's talk about parameter number 1, the filling ability. This rheological parameter is measured by the ability the self-consolidating concrete has to fill spaces of formwork of any shape or size under its own weight, eliminating the need for mechanical help like vibration. Next, we're going to talk about parameter number 2, the passing ability. This rheological parameter is measured by the ability the self-consolidating concrete has to flow under its own weight within the formwork that contains obstacles like reinforced bars, and like the filling ability, this is accomplished while not having any help from vibration. And finally, the last parameter, parameter number 3, the resistance to segregation. This rheological parameter is measured by the ability that self-consolidating concrete has to stay consolidated together on its own, keeping its strength and not losing any load capacity or durability. This is accomplished by reducing the water content in the mix and adding a fine powder to the mix, like fly ash or limestone filler.
Hello everyone, my name is Kevin Richers. We're going to start off today by just going over the difference between the mechanical properties between SCC, which is self-consolidating concrete, versus the conventional concrete that most of us are used to. So the two big things that you'll get out of self-consolidating concrete are workability and stability. To think about workability, that's the ability for that concrete mixture to get in and around all those different rebar and into places that are difficult with typical concrete, right? So that's a big advantage. Less labor is involved, and it does this actually through taking advantage of high range water reducing admixtures versus conventional concrete using additional water, which would in turn weaken the concrete over time. Another big thing is stability to look out for in concrete. SCC is great because it has less coarse aggregate than conventional, and because of this, it's more fine and it's able to resist segregation. Also want to dive into the long-term durability of SCC concrete versus conventional concrete. SCC is actually going to be a more dense mixture, and it's going to have more isotrophy, which you can think of that as homogeneous mixture being more consistent throughout, more consistent results, exactly what we want to see in the field. customers love consistency. Surface quality is another big thing that you'll get out of SCC. And then strength, of course. You can see compressive strength testing to the right here. Tensile strength is going to be the opposite, right? Pulling up and down on the concrete. And then we'll move on to the negatives of using SCC versus conventional. Obviously, we spoke a lot about the pros. There's also, quite a few cons out there actually too. Number one, of course, it's costly. Those additives and materials are upfront costs, and they are more expensive. The additives, include such thing as surfactants, and then also the modifying admixtures, the VMAs. So those are things to definitely look out for. Those surfactants are really going to help lower your rheologies, and that's what's going to allow your concrete to be so fluid. More negatives. Also, it's definitely going to be more technical for those, actually all phases of the design to transport to implementation to batching. You're relying pretty much on the materials themselves to consolidate versus conventional tools to consolidate the concrete and get it to where you need to. So that's a big difference, right? And then your loading and mixing monitored. Everything is going to be monitored more closely to get that optimal dispersion that you need. That's just part of the game here. Higher formwork pressures could also be seen because it is more flowing, and you could see higher pressures. And because of this, you actually might have to strengthen your formwork on site. So additional labor there. Also, some negatives, it's more sensitive to fluctuations with both water content and raw materials. So you could think of water concentration, it's already hard to get right. So having less room for error is going to be, harder to maintain. You're going to need more experts in the field to get this right. And also, one thing to note is, I'm showing some pictures of cement plants for a reason here. This is actually in Cleburne, Texas, not too far from where I'm at. And you can see that kiln, rotating kiln, that's where the clinker goes through, and that's what that flame there, creates the clinker. And that flame, depending on the time of year, is actually powered by different fuel sources. And depending on the fuel source, that flame could be hotter or, less hot. And also the air inside that kiln could be different too. And all that affects the cement properties. And if you're not, keeping up with your quality assurance and quality control, then you have, you got to get everything right to get the SCC slurry properties that you need. So there's a lot of things to consider here than just paying a little extra. There's a you need experienced personnel to get the mixture here. Also, there's some negatives of using SCC, like different functionality requirements to look out for, such as passing ability, resistance to segregation, and also increased shrinkability. And there's more testing involved. There's a slump flow test, there's a J-ring where you need to show that it can get around these rebar, and a column test where you're measuring different parts of the column and comparing them afterwards. So that's a wrap for my section.
Conclusion. To summarize everything that we have presented today, you can see how self-consolidated concrete is a valuable asset to the construction industry. From its real-world applications such as high-rise buildings, bridge construction, precast concrete elements, and so much more. Self-consolidating concrete eliminates the need for mechanical consolidation like vibration because it is a highly fluid mixture designed to flow and consolidate under its own weight. Self-consolidating concrete relies on gravity to self-compact, self-level, and self-place. The filling and passing abilities allow self-consolidating concrete to be useful in almost any circumstance. Self-consolidating concrete may be more costly than conventional concrete, but it is more consistent, has a higher surface quality, and because of its resistance to segregation, it has a higher compression and tensile strength. Its workability is better, and because it has less coarse aggregate, it's more stable than conventional concrete.